So before we get to our notes today on standing waves, let's go ahead and go over today's warm-up question, which provides you with a graph and asks you to find frequency of the wave in the graph and then to identify how changing the amplitude of that wave, specifically doubling it, will affect the wave's energy, frequency, and wavelength. So let's go ahead and take a look at these questions, starting with the wave frequency. So here's that graph, and you can see that on the y-axis we're measuring basically the amplitude. It says height in centimeters, but the amplitude of that wave, and on the x-axis we're measuring the time interval that has passed. And so in order for you to find frequency, you need to obviously know what frequency is. And if you go back to that definition, the frequency of the wave or the number of wave cycles that pass by per given unit of time. So it's typically cycles per second, and we measure that in hertz. Hertz is if you're using seconds, so cycles per second would be in hertz. And so this graph is in seconds, and so we could find the wave frequency in hertz. I just need to know how many waves pass by per second. Well, in 1 second, I'm right here on my graph, like all the way toward the left-hand side. And I know that this is only a very small fraction of a wave. Okay, so if I had like one full wave in 1 second, that'd be easy. I could say my frequency is 1. But because I have this indistinguishable amount of a wave, I don't know exactly how much that is, I need to calculate it. And again, if you remember the definition, and you know that it's number of waves per time, then you can just take the number of waves and divide it by the time. You could use the total number of waves going all the way to this point divided by the total time, or pick a point on the graph where you can see where a wave ends and use that point, which is what I'm going to do. I'm going to use this point right here at 20 seconds because that is where one wave ends. And so if I wanted to divide the number of waves by time, at 20 seconds I have one wave. 1 divided by 20 would give me my frequency of 0.05 hertz. So the answer to number 1 is 1/20th of a wave, or 0.05 hertz. So that's how many pass by per second. And again, that makes sense because in 1 second I have definitely had some small fraction of a wave at this point, and that is definitely a small fraction. All right, second question. If you double the amplitude of this wave, find its change in energy, its frequency, and its wavelength. Okay, so change in energy. First of all, let's talk about doubling the amplitude. You'll notice I sketched this graph, and this wave does now have double the amplitude. It is taller. That is the only change I made to it, is by making it taller. Okay, and I do know from the equations that we learned last week or earlier this week that we talked about how energy and amplitude do have a relationship. In fact, it's written on my board that the energy of a wave is proportional to its amplitude squared. So if I double the amplitude, I am going to get more energy, but it's not going to be 2 times as much. It's going to be proportional to 2 squared, or 4. Okay, so if you double the amplitude of a wave, it will have 4 times the energy. We talked about this relationship a few days ago. We discussed how it affects things like tsunamis. Having all of that additional amplitude or height to that wave, those carry a lot more energy, and therefore they can do a lot more damage to surroundings. What about frequency? Well, I didn't change the time that it took for one wave, which means I also didn't change the frequency. All I did was change the amplitude. Amplitude and frequency are not going to be related to each other. Okay, so making that change to the amplitude has no effect on frequency, and similarly, it also has no effect on wavelength. The only thing changing the amplitude will affect is the energy of that wave for our mechanical waves, which is, again, what we're focused on this unit. These are your answers to the warm-up, so please make sure that you have entered these in MyOpenMath. Does anybody have a question about today's warm-up? All right. Again, we are going to take notes today on standing waves. So if you are trying to work ahead, I'm going to recommend that you don't do that because you're probably going to start missing some stuff. So there are some things in here we need to go over so that you are prepared adequately to answer those questions in that assignment. So again, I would take notes if I were you because there is quite a bit of information in here. And once you get the hang of it, I promise it won't be too bad. But we're going to start with what is a standing wave. And here's a video demonstration of a standing wave, and then we'll talk about it a little bit more after that.
Standing waves are a result of reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode. Sending the pulse at twice the frequency results in the second harmonic. If I triple the frequency, I get the third harmonic.
So he's introduced some terms we haven't talked about yet, and that's okay. I just wanted to show you this. But when we talk about a standing wave, it's going to be a wave that effectively looks like it's stationary. It is a result, as he mentioned, of reflection and interference. And that pattern and that interference makes it look as if the wave isn't moving. So here's your definition for standing wave. It is a wave that does not appear to travel. Also called a stationary wave, it is made when a reflected wave constructively and destructively interferes with an initial wave moving in the opposite direction. This overlap produces stationary points in the medium and sections of the medium where there are oscillations that move up and down. If you take a look, you can see in the background, and y'all have seen this animation before, but you can see in the background this initial blue wave moving to the right-hand side of my screen. And if you imagine it reflecting at this point, that's what this red wave is representing, is the reflected wave. And those two will interfere with each other. Okay, and that interference is going to give you points that are stationary, like this red point right here, and also points that are oscillating with these maximum amplitudes, like this one that I'm kind of tracing right here with my cursor. So again, this is a standing wave. And you just saw him do this with a string, okay, between him and his assistant or friend or whoever that was, getting that string to look like this. Okay, and so we're going to talk about names for these different parts. We're also going to look at some other examples of standing waves that are generated by a machine that moves much faster, and then you can see it a little bit better than you can in the example that we just looked at. Okay, so in order for a standing wave to form, there are some criteria that have to be met. Because it is the combination of two waves that are moving in opposite directions, and because it requires this constructive and destructive interference in order to produce this, you have to have waves with equal wavelength so that they can overlap and have the exact same length in order for one part to be adding up while the other part's canceling out. They do need to overlap perfectly, which means they need the same wavelength. They also therefore have to have the same frequency. They need to have the same amplitude. If they don't, you won't get those stationary points because they won't cancel out entirely. Okay, they also need equal speeds, and they have to propagate in opposite directions. So they need to be moving, basically the waves moving one way, its reflections moving the other way in order for them to overlap and produce that pattern of, again, those stationary points and those areas of oscillation, which I'm going to give you a name for in just a second. By the way, if I do go too fast and you don't have enough time to write down, you can open this on your own screen. I am currently on slide 79. Okay, so I told you we were going to give you names for those different points on the wave. So node is the first term you need to know, and these are the areas on a standing wave that are constant and do not change, where you have zero displacement. They're formed from destructive interference, where the crest of one wave overlaps with the trough of the other. And these are the points where the wave is not moving. On my screen right now, they're the points in red, which here, I'll highlight them for you. Okay, those are your nodes. Okay, and if you pick, just pick any of them, I can pick this one here in the middle. If you take a look at the wave and its reflection in the background, you can see that at every point, those two waves have equal and opposite amplitude, or they might both be at equilibrium. But in either case, they're either canceling each other out or there's nothing to add if they're both at equilibrium, and that's why this point doesn't end up moving. So you get nodes from this destructive interference, and you get that destructive interference in this perfect pattern when you have those waves meeting the criteria that we just talked about on the previous screen. There are also names for the portions of the wave that have those maximum oscillations, where you see our maximum amplitude and our minimum amplitude, and those are called antinodes. So antinodes are the areas that fluctuate the most on a standing wave. They're these areas right here that I've just highlighted in green. These are positions of maximum displacement, and they're formed by constructive interference. In other words, you can follow one of these and you can look and see that when it's at its highest point is when the crest of one wave in the background overlaps with the crest of the other. Or look at its lowest point and you can see troughs overlapping with troughs. But in either case, you're getting this due to constructive interference. And these are the points where the wave is moving up and down because of that constructive interference to give you this pattern. Okay, so again, nodes and antinodes. Nodes are created by destructive interference. Antinodes are created by constructive interference. And you can see them forming this nice pattern, which gives us a standing wave. Okay, so another term that he mentioned in his video was fundamental mode or fundamental frequency. Fundamental frequency is the lowest frequency that is produced by the oscillation of an object. It's also called the first harmonic, and you heard him also use the terms harmonic. Okay, so we're going to talk about a bunch of terminology today as well. But if you were to attach a string between two rods and then just pluck that string, it would vibrate like this. It would look kind of like a jump rope. And that's what you saw in the first wave that he made. It looked like a jump rope. That was the fundamental frequency or fundamental mode or first harmonic, whatever term you want to use. Okay, and so that's the lowest frequency that can be produced for that object. The harmonics, when he talked about the second harmonic and the third harmonic, and we could keep going with that list, are all multiples of the fundamental frequency. So if you have a vibrating string or a vibrating column of air in certain types of instruments, okay, they will vibrate at all of the harmonics of the fundamental. And again, we're going to talk about these terms more as we look at some examples. So the first thing I'm going to show you is an example where the standing wave, instead of somebody just trying to oscillate the rope by hand, it's going to be generated by this oscillating device, and he has a tone generator here that can change frequencies to make it oscillate at different rates. And when this happens, it actually moves quite a bit faster, and you can actually see the wave and the reflection at the same time. And so it's pretty cool to look at, and this is typically how they're drawn on paper as well, if you're taking a paper test or quiz or whatever, or even if you're just looking at a still image on screen for your assignment today. So I'm going to show you at least part of this clip, and then we'll talk a little bit more about it as we go over some of this terminology for a standing wave.
Okay, so next I'm going to turn on the function generator, and we'll take a look what happens. Right now it's set to just over 10 cycles per second. So you can think of that as 10 times a second, this thing is moving up and down through one cycle. When it does that, the wave travels down the string and bounces off that end with the pulley and comes back to here. But it just so happens that I set this up so that in the time it takes for that wave to go down to the end and bounce back, right when it gets here is when the next cycle is starting from the
So this is that fundamental frequency. It looks kind of like a jump
rope.
rope.
Each wave builds on the previous one, and you end up with this energy buildup and this thing bouncing away like this.
That's in slow motion.
So that's the thing with the standing wave pattern like this, it relies on some very specific conditions being met. Namely that the time that it takes for the wave to go all the way down and back is the same as the time between cycles here. So each consecutive wave that goes down and comes back adds up with the next one from the function generator. And that's why this energy builds up to this large displacement like this. So if we change the frequency,
Sorry, Sorry, this thing is moving really slow for some reason. I paused that for a
We changed
second.
the speed of waves.
Okay. So I'm going to let that try to load because it's moving really slow. But he's at the fundamental frequency, and he's going to change the frequency on that machine that he has over there. His fundamental is about 10 hertz. So in order for him to get the second harmonic, and it said this on the definition, but it's a multiple of the first harmonic. So if he's at 10 hertz, he should see the second harmonic at about 20 hertz. So let's see if that happens, if I can get this video to load right.
We can change either one of those, and that equality won't be true anymore. So if I come
sorry.
over here to this side and I pull down on the string.
So the first thing he's actually changing is he's changing the medium.
You can
He's
see
increasing the
The
tension.
string's still kind of bouncing around some, but we don't have that big pattern anymore like we did.
I don't know why this video is
When I
being
let
so
go,
slow.
it builds back up because we're still putting the energy in from the function generator. So when I pull down on the string, I'm increasing the tension, which speeds up the waves. So then they get down and back faster than they were before, and they don't add up anymore because they're getting back too early. Similarly, I can lift up, slow the waves down, and then they're not adding up because they're taking too long to get
So
back.
I told you guys that the speed of a wave depends on the medium. So when he changes the tension, he's actually changing the medium, and he's making the waves move either too fast or too slow so that they don't add up. So now he's put it back to normal, and I told you that he's
So the frequency
he's
of-
trying to find the second
I can see
harmonic.
when I change it
It
too
should
much,
be
we'll still get some oscillation.
around 20 hertz.
But once I get to sort of 11-ish,
You don't have the
it's
same
bouncing around,
pattern
but nowhere near.
that you had before. The string's not moving nearly as
But
much.
I keep going up. 12, 14, 16. Okay, something's starting to happen now on the string. And that's getting a little louder. If I put it right around 20,
So you can
take a look,
actually
and
see
now,
the wave
instead of
and
a
its
half wave
reflection.
fitting on the string, we're fitting a whole wave. So that means by the time one wave.
All right.
goes out-
So again, you can see both the wave and its reflection at the same time because it oscillates so much faster. But that's his second harmonic, and he got that at about 20 hertz. I'm going to move on from this video because it's moving a little bit slower than I want it to. And we'll use the other video that I have in here to help look at them. But the first harmonic, again, we saw this. It's the one that looked kind of like a jump rope. It's the lowest frequency that the object can oscillate at. And it's really just half of a wave. If you look at this picture, again, I know you see that half and its reflection, but you're only looking at like how many wavelengths looking at one of those. That's only half of a wave. Okay, so your first harmonic, again, looks like this. You have 2 nodes and 1 antinode. And so I've labeled those here. If I were you, if you're trying to take notes on the harmonics, maybe make a table, and first harmonic can be the first column, and then second harmonic and third harmonic, and you can have rows in that table for number of waves, number of nodes, number of antinodes, something like that. Okay, or however you want to do it, but we are going to take a few notes on some of these, and it might be helpful to organize it in a way like that. So again, you've got half a wave here. It has 2 nodes. It has 1 antinode, and its frequency is F, whatever the fundamental frequency is for that object. In the video we just looked at, the fundamental frequency was 10 hertz. However, a different string with a different tension or just a different material would have a different fundamental frequency. So it depends on what that is. It's not always 10. Okay, but in the example we just looked at, it was. So its frequency will be F, whatever that is. The second harmonic is going to look like this, and we saw this in that video clip as well. But you can actually see 1 full wave and its reflection on that string. And you can see 3 nodes and 2 antinodes. If you're trying to figure out what harmonic you're looking at, guys, count the antinodes. Count these areas of maximum oscillation. There are 2 of them. This is the second harmonic. The third harmonic is going to have 3, and so on and so forth. And the frequency of my second harmonic will be twice my first. So if my first harmonic is 10, my second harmonic is 20. Okay, but it will be double whatever the first one is because they're multiples of each other. The third harmonic, again, I told you can count those antinodes, is 1.5 waves. It has 4 nodes. It has 3 antinodes. Okay, and it has a frequency of 3F. So if you kept watching his video, and you're more than welcome to watch it on your own screen if you want to, since it wasn't working very well on mine. But he does show the third harmonic as well. And the third harmonic for his is about 30 hertz because his fundamental was 10, so it's 3 times that value. Okay, fourth harmonic, again, if you haven't noticed the pattern yet, you should. Okay, it's the same thing. We're just adding half of a wave each time. We're adding a node and an antinode each time, and we're multiplying by a different factor for our frequency, 1 more each time. Okay, so my fourth harmonic, I have a total of 5 nodes and 4 antinodes. The frequency will be 4 times the fundamental, and there are a total of 2 full waves on the string. Okay, we could keep going. There's not like a maximum harmonic that we can go to. Okay, but there is a point at which it just becomes really hard to see anymore. And there's also a point at which, we don't really need to write this because it's the same pattern. Y'all can figure it out from there, hopefully. Okay, so here's the other video clip. I'm hoping this one plays better than the last one. And you're going to see the same pattern in the string that he uses here. His doesn't have any sound, so I'll just talk over it. But he has the same type of wave generator that's causing oscillation of this string. And for his fundamental frequency is 4.7 hertz. So his first harmonic or fundamental frequency is 4.7, so a little less than 5. So his second harmonic is going to be twice that. Okay, so it's going to be a little under 10. Okay, 9.4 specifically is what he should get for his second harmonic. And that's what he's trying to do right now, is trying to get it timed right so he can see those 2 antinodes, and there they are. You can see the 2 antinodes. It's, again, moving a little slower on the screen. But you can see the reflection and the initial wave at the same time. And it is exactly 9.4 hertz. I would expect the third harmonic to be 4.7 times 3, which is going to be 14.1, a little under 15. Okay, and again, he's adjusting his device to try to get it there. And let's take a look at what he writes. So I'm pretty sure it is 14.1. It is. In fact, if I fast forward this video, you can see some of these higher harmonics, and look how tiny these things look now. But you can see both the wave and its reflection. It gets harder to see as you add more of them to the string, but you can theoretically add, as many of them as you want. You just won't be able to see it very well. Okay, so it's the same pattern that we were just looking at. You're adding half a wave each time, and you can count those antinodes, you can count those nodes. It's the same pattern of multiples of that fundamental. So that's what this question is asking. It says, compare the frequency of the fundamental, that's your first harmonic, with the frequency of the overtones. You might want to make a note that the word overtones is just used for anything beyond the first harmonic. So the second harmonic, third harmonic, fourth harmonic, so on and so forth, are all referred to as overtones. Technically, the second harmonic is the first overtone, okay, and then it would go from there. We don't typically use the word overtones in here. I'm just introducing you to it in case you are watching a video elsewhere to study or whatever else, you might see that referred to. But the pattern we noticed, we just looked at it. The frequencies of the harmonics are multiples of the fundamental frequency. So if the fundamental frequency is, let's say, for example, 8.5 hertz, then the second harmonic or first overtone would be twice that. 8.5 times 2 is 17 hertz. The third harmonic would be 3 times that. You can multiply it by 3. Okay, 25.5 hertz, so on and so forth. All right, so how do you think changing the tension of the string would change your results? So the first video, he actually showed this. When you change the tension of the string, you change the medium. And when you change the medium, you change some properties of the wave, including its velocity. Okay, but there are different factors that affect these your fundamental frequency and that affect these harmonics. And you do need to be familiar with these, so I would add these to your notes. If you play a musical instrument, especially a stringed instrument, this is really easy for you to understand probably. Okay, because if you play a stringed instrument, you would know that longer strings are going to make lower frequencies of sound and vice versa. They're going to have a lower pitch to them. Okay, even if you don't play an instrument, if you think about the sound that would come from a guitar versus a ukulele, those shorter strings with that shorter neck, it's going to be a higher pitched sound than a longer string would be, or a harp would be a really good example, because they have varying lengths. But longer strings make lower frequencies and vice versa. Tighter strings make higher frequencies and vice versa. Again, if you play a stringed instrument, you know this, because if you have to tune it, you have to tighten or loosen those strings. And that is going to change the pitch, which will correspond to the frequency. We're going to talk more about sound later on, and that will help with that. But tighter strings make higher frequencies. Thick, heavy strings make low frequencies and vice versa. So the thicker that string is, the lower that sound will be, that lower that frequency will be. And conversely, the thinner it is, the higher it will be. Again, a guitar is a good example because the strings do vary in thickness, and the thickest one is the lowest pitched sound, and therefore the lowest frequency as well. So again, be familiar with some of these factors that affect the harmonics of like a stringed instrument, okay, for example. Or just a standing wave. We don't have to be talking about an instrument. You can be looking at the one that we just looked at. So here is a question, an example question that's similar to some of the ones in your assignment today. And it's one that might give you trouble if you're not listening right now. So if I were you, I would copy this down so you can refer back to it. It says, a harp string has a length of 0.85 meters. If the string is vibrating with a wavelength of 0.17 meters, what harmonic is it vibrating at? So even though the harp string is 0.85 meters, that is not the wavelength of the sound being played. It says that the wavelength of the wave that's being played is 0.17 meters. It's vibrating at that wavelength. So I want to know how many waves will fit on my harp string. I can just divide. My total length of my string is 0.85 and my wavelength is 0.17. That's 5 wavelengths. Okay, and so for me, I'm visual. I'm going to draw that. So I'm dividing this into fifths, but here are the 5 sections, and I need to put a full wavelength in each of these sections. So it's going to look something like this. Full wavelength and its reflection, because we're dealing with a standing wave. Okay, and so if I look at this and I want to know what harmonic it's vibrating at, well, now I can just count, because we already talked about how we could just count those antinodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the 10th harmonic. Okay, or again, you could also remember that your harmonic is going to be twice your number of wavelengths. So if you have 5 wavelengths, multiply that by 2, that's going to be your 10th harmonic, because remember, you're fitting 2 different antinodes in here for each wave. So questions about this one? You're going to see one just like this on your assignment. Okay. You can look back at it if you need to. So here's some other questions. They're similar to things you might see. Which wave has 4 nodes? Guys, take a look. I have 4 lettered pictures up there. Which one has 4 nodes? A, B, C, or D? C. Don't count the antinodes, count the nodes. There are 4 of them. You have to count the ends, okay, and these 2 points in between, but that's 4 nodes, so wave C. If the length of the string shown is 2.5 meters, what is the wavelength of the standing wave vibrating in the 3rd harmonic? Image C is my 3rd harmonic. Okay, it says the length of the string is 2.5 meters. Well, wave C has 1.5 waves on it, not just 1. So the wavelength isn't 2.5. 1.5 waves is 2.5, so what is 1 wave? Again, you can do this. Total length divided by total number of waves. That's 2.5 divided by 1.5 waves. And that gives me a wavelength of 1.6 repeating, which I rounded to 1.667 meters. Okay, so the wavelength of that wave in the 3rd harmonic based on this information is 1.667 meters. Questions about this one? Again, you have to be able to do this as well. You will see it again. All right, follow up. If the fundamental frequency of the standing wave is 13 hertz, what is the frequency of the 3rd harmonic? So if my fundamental is 13, that's wave A. What is the frequency of wave C, my 3rd harmonic? Again, it's multiples. So if the fundamental is 13, 13 times 3 is 39, and that would be the frequency of the 3rd harmonic. Okay, so again, we talked about this. We saw this pattern in the videos as well. But let's answer the other question. What about its velocity? Well, now I know the frequency of this wave. In the previous question, I found its wavelength. So I can just multiply wavelength, 1.667, that I found in question 2, multiply by the frequency that I just found, times 39, and I get a velocity of 65 meters per second. So again, you might be asked to do that. That takes a couple steps to get there, so be able to answer questions like the ones we're going over. Again, if you want to look at these, again, I'm on slide 93 right now. All right, the frequency of D is 4 times that of A. How does its wavelength compare? All right, guys, which one has a longer wavelength, A or D? Let's start there. Which wave is longer, A or D? Yeah, you were right with your made-up sign language. A. Wave A is longer, guys. Wave D, look at this wave. You can fit 2 whole waves on this string. That means they have to be shorter. Wave A, you can only fit half a wave on the string. Okay, so if I'm trying to compare the wavelengths, I really just need to know the relationship between frequency and wavelength, and I can see that relationship in this equation. I can also just look at the picture. But velocity is wavelength times frequency. And since the velocity is going to be the same for both of them because it's the same medium, it's the same string, okay, then that means we just need to look at the relationship between lambda and f, between wavelength and frequency, and they will be inversely proportional to each other. So if you have 4 times the frequency, you are going to have 1/4 the wavelength, which makes sense because this wave is much shorter. It is 1/4 as much. In fact, there's 1 here and I can fit 4 here, okay, of those antinodes. If you're counting those, you can see that fraction. So again, if I wanted to answer how the wavelength compares, wave D has 1/4 the wavelength of wave A. Or you could say wave A has 4 times the wavelength of wave D. Either way. All right, guys, for the rest of your class period today, you can work on your assignment 1302.4, Standing Waves Problem Set. It does have questions that are similar to some of the ones we just went over, so you might want to have your notes out, or if you didn't jot all of that down, open up the slides and look at it. If you don't finish this in class, it will be homework. It is due by 11:59 p.m. tonight. So again, go ahead and get to work. Help each other out. If you have questions, please let me know.